are what we refer to as fixed and random effects models. And so just to get a quick poll of the audience, how many of you have seen the term fixed effects or random effects models before? Okay, so we've got a few of you, primarily a lot of those that have been around a little bit longer and have done some research in this domain. So we've got some good familiarity there. And so I'll talk, the first slide just talks a little bit about the nature of transportation data and a few of the problems we run into. We've touched on some of these at various points over the semester. We'll talk a little bit about what we refer to as panel data, which is where fixed and random effects often arise. Some of the issues that come into play that make estimation of models with panel data problematic. And so I guess just to clarify, when we talk about panel data, it means we've got the same group of individuals who are observed at multiple times. And so they're referred to as a panel. And so we've got repeated observations on the same individuals over time. And there's a lot of context as that comes up in survey work, in general observational work like the crash analysis we talked about previously. And so in those settings, we have two general approaches where we try to account for the correlation we see when we observe the same individual multiple times over the course of an analysis, because we would expect if that individual or that observation tends to have higher than average values or lower than average values during one period, that same general trend is likely to occur over subsequent periods. And if we don't explicitly account for that fact, and this is very similar to when we talked about the paired t-test, for example, way back in the early portion of the class, we could potentially again run into issues where we're not appropriately capturing the variability within and across individuals. And then we'll conclude very briefly. We won't have time to get into this in great detail, but there's a related concept, random parameters or random slopes. And so that is where we're going now. And so as we think about some of the different issues that arise in transportation engineering and transportation research more broadly, there are a host of different problems. And so one of those is oftentimes we're dealing with data that are non-random, okay? So if data aren't randomly sampled, they may not be representative of the population. And the degree to which that is a problem will vary significantly. But you need to keep in mind, if it's not a random sample, we can't just implicitly assume that whatever results we see from our analysis or from our regression models are then going to apply broadly across the population, okay? One of the bigger problems that may arise is we may have some type of selection bias that's related to that non-random sampling. And so, for example, in the best case, we'd like to collect our data in a census style, where we're actually able to observe every household in the United States, right? Now, there are other approaches that are probably more convenient, and one of those is what we're referred to as a convenient sample. And so we could just go to any random place. I use the term random loosely, I guess. If we wanted to collect data about individual households, we could go to Michigan State University to do that. We could go to a sporting event. We could go to a city hall meeting. We could go to a county fair. We could go to a whole bunch of different sites to try to sample individuals. But some of those sites are probably not random snapshots, random samples from the broader population. And so as a consequence of that, what tends to happen is we may have some biases that we're completely unaware of that are just reflective of the fact that we're sampling from a group that is somehow different from the population. And so in the case of individuals like that, maybe we have a disproportionate number of males or females or persons of a certain age, persons of a certain political affiliation, just general differences that may cloud the results that we would obtain there. And so those are a few things to be careful of. And so at minimum, oftentimes it's not clear to us how random our sample is. And so as you're preparing your research paper, you'd want to talk about how your data were sampled, how the data were acquired, because at minimum, that would give your reader the opportunity to assess whether there are any potential concerns related to the sampling plan or the nature in which those data were collected, okay? Another concern that we touched on in the preceding discussion between Poisson and negative binomial is unobservable heterogeneity. And so all this means basically is we've got additional variation in our data. And what happens occasionally, and the biggest concern here is what we have when we have what's referred to as omitted variable bias. Okay. And so if you have an important variable that just you're not able to observe for whatever reason, and we actually do have such a variable in the preceding analysis we worked through with the crash data, because one very important factor we didn't have information about was the traffic volume and the number of motor vehicles that were present near those K through 8 schools, right? And so as a consequence of that, we had information about the population. So maybe the population in that community serves as a reasonable proxy for the amount of motor vehicle traffic, although that assumption can be somewhat tenuous. And so the implications of that would be, well, what if we're not observing traffic volumes, but those traffic volumes are likely to be correlated with some of the other factors, like the National Functional Classification of the roadway. And so we had seen some differences between arterials and collectors and local roads. And since those arterials serve higher traffic volumes, we're sort of implicitly capturing volume as a part of that. And so it's difficult for us to determine then what that variable actually means. We can use it for predictive purposes, and we can start to drill down to understand what it may be reflective of. But unless we have a clear understanding of the factors that are, in this case, generating or leading to crashes, and that becomes a real big problem for us. Another interesting example, and you've seen previous presentations this semester about naturalistic driving study data. And a question that I almost always get when I present on that data is, well, don't the subjects tend to behave differently if they know that they're being observed? And so we refer to that as the Hawthorne effect. And so as a consequence of that, if people behave differently when they know they're being observed, then that really creates some concerns when we try to draw inferences from some of these studies where we're monitoring driver behavior. In the case of the naturalistic driving study, what the research generally shows is there is a Hawthorne effect, but typically that effect dissipates anywhere within 2 days to 2 weeks of the subject enrolling in the study. So after a short while, there's perhaps the driver is somewhat paranoid or less likely to engage in high risk or illegal behaviors. But over time, they essentially more or less forget that they're being monitored. But that's something you should take into consideration, though, if we're observing people observations over relatively short time periods. This could be a very important impact. And so we'd want to, for example, make sure we're observing the subjects for a sufficiently long period so that that effect is largely washed out to a degree, or they start reverting back to their normal behavior. But that's something that arises relatively frequently with transportation, where we often test out different types of devices and test out different strategies. And we're doing a study right now where we're monitoring distracted driving. And so we have students who are basically watching drivers as they travel past intersections and recording whether or not they're wearing their seatbelt, whether they're using their cell phone, etc. And we have had a few cases where people get a little paranoid about that. And so as a consequence, their behavior may change as a result of that. Now, it would be a particular concern there if we're observing seatbelt use or distracted driving, we may actually influence whether they're belted or driving distracted. And so as a consequence, what we do there is we try to observe the vehicles as they're moving before they get to the intersection. So there are ways that we can try to control for this in practice, but this is something that is sometimes unavoidable in transportation research. Another area that's very unique to transportation, and I guess this is really true in other fields as well, but there are a lot of experiments that are impossible or at least impractical for us to try to run from either a feasibility or an ethical standpoint, okay? And so if we're looking at different things that we'd like to test out, we typically can't run that as a random experiment. And even in the case of the naturalistic driving study, we wouldn't have the capability to instrument and put video cameras and recording devices in individuals' vehicles. Okay, we'd be looking for volunteers as a consequence of that. And so then getting back to our initial point, are those volunteers a purely random sample of the broader population? Probably not. And when we look at different types of treatments to apply or hypotheses we'd like to test out, like there's a lot of work right now that's looking at, rather than fuel taxes, taxing people based upon how much they drive as a consequence. And so that's something where we're basically, volunteers have been recruited across these different states, because that's not necessarily something we can force on individuals, at least in the near term, in consideration of differences in income levels and other factors that would make that somewhat challenging. Okay. So all of these are just important things to consider as you work through your projects and in any future research, whether that's transportation related or otherwise. But we'll drill into a few of these in greater detail that are pertinent to the work we're talking about today in this lecture. Okay. So when we look at natural experiments, or quasi-experiments as are typical in transportation. These are very similar to random experiments, except observations often fall into the treatment and control groups naturally, instead of being randomly assigned by the researcher. And so that gets back to the preceding case. And so if we think about some of the safety research that we've seen presented, ideally, if we want to know how effective a certain treatment is, if we install rumble strips, or we install median cable barrier, or we convert a signalized intersection to a roundabout, we typically would look at what changes occur between crashes before and after that treatment is applied. And we'll often like to use a control group that is unchanged, so hasn't been converted, hasn't seen that treatment installed, to help us determine how effective those different treatments are. Now, ideally, what we'd like to do, if we wanted to know how effective those different treatments are, we would assign them randomly. Okay. Now, from a transportation agency's perspective, a lot of people would probably be upset if you just randomly determined where you're going to install roundabouts and some of these other treatments. So generally speaking, there are certain conditions, and that could relate to traffic volumes or other factors that would determine when and where these treatments are applied. And so in that context, we want to be somewhat careful about understanding whether or not those distinguishing factors are also random in nature. Okay. Now, the big thing we wanted to talk about as a part of this lecture is what we refer to as panel data. Okay. And so when we talk about panel data, we'll also see that referred to as longitudinal data. So we're observing the same individuals, the same units at multiple times over time. And so that combines two different types of data. So time series data. So anytime we're conducting repeated observations over time on a unit, we refer to that as a time series analysis. And we combine that with cross-sectional data. And virtually everything we've talked about up to this point in the course has been cross-sectional data. We're taking a cross-section of the population, or we're taking a cross-section or a sample of some specific group of interest. And what we're doing basically is we're observing the exact same variables on the exact same cross-section over at least two and oftentimes more periods of time. Okay. And so we refer to these data as panel data, and these data are particularly useful to us for several reasons. If we think about some of the challenges that arise when we're conducting statistical analyses. So first and foremost, and this is not necessarily the primary motivation here, but if we're observing panel data, that in essence increases our sample size. And so that works to our advantage, and it makes it more feasible for us to design experiments such that we would be able to identify an effect when it actually is there, for example. So minimizing our likelihood of conducting a type 2 error. It also provides important insights into questions that can't be answered using just a time series analysis or cross-sectional analysis. And this relates back to some of the content that Professor Mannering had presented at the transportation seminar 2 weeks ago, because some of these individuals, their behavior may change over time, right? And that may be true of various different research questions we're investigating. And so if we don't have access to panel data, we're just observing persons at one point in time, we can really only make inferences as to that one snapshot. And so a consequence of that, and we keep coming back to the variance point, if we're observing the individual just once, we're probably not doing a good job of capturing the variability that's inherent in those decision-making processes. One of the big benefits in using panel data is it allows us to circumvent some of the omitted variable problems that we see otherwise. And so as an example, if we think back to circumstances, even in the case where we worked through the crash data a short while ago. So we know that there's certain important variables that are admitted and not observed by us, okay? And one of those being traffic volume. So one thing we could do, we could assess that in effect if we've got 5 years of data. Now for our analysis purposes in that example, we aggregated all 5 years. But if we look year by year and we observe the same location 5 times, we can basically control for some of those site-specific factors, okay? So if there's something that we're not observing at a site, this is kind of like the paired t-test analogy. We can look at how the number of crashes changes within that site over time. So we're implicitly then accounting for any of the other factors that aren't actually captured in our model because they're constant across that site. Okay, so we won't be able to determine what the magnitude of those impacts are, so how much traffic volumes impacted crashes as an example, but we would at least know that those traffic volumes are similar at that site, and so we've conditioned out that effect as it were. Okay, it's kind of how this works when we're working through and analyzing panel data. Okay, and so as we think about that, there are several different types of variables that we run into. Now, some of those are variables that might vary between individuals, but they don't change over time. And so driver's characteristics, so a person's gender or a person's height, well, I guess depending on the time scale, some of those things could change, but so individual characteristics, roadway characteristics, again, with the caveat, unless we've introduced a construction project or something of that nature. But if we're observing intersections or road segments, those tend to have consistent characteristics. And if we observe those over time, individual persons or individual road segments would be different from one another, but they wouldn't change intrinsically themselves. They'd be the same over time as we observe. Okay, so there's some advantages there. We also have variables that change over the time, but are the same for all individuals. And so examples there in the transportation community, we have laws for seatbelt use, for helmet use, for distracted driving. And so these laws can and do change over time, but those changes apply to every individual in the time across that sample at that same time period that we're conducting that observation, okay? And so that's advantageous because we can then try to assess, for example, the effectiveness of a helmet use law, where Michigan's was repealed or weakened roughly a decade ago at this point. And so we could observe all of the motorcyclists with and without that law in effect. And so there are advantages to that as well. Then we also have variables that vary both over time and between individuals. And so how fast we drive, whether we're appropriately licensed, a person's age, as an example, these are all things that vary across persons, and then also within those persons over time. And then lastly, we have variables that do vary, but in predictable ways. And so age would be one subset of that. So while if we conduct repeated observations on the same individuals, we know that in each subsequent period, that person's going to be older, but it's very easy for us to account for that because we know going in what those changes would be in essence. Okay. And so if we look at our general linear regression model that we're working with, we've got a response variable, which is equal to an intercept. We've got slope term. We generally refer to variables as having fixed effects. And so we'll circle back to that momentarily. And then we also have an error term in essence. Okay. And so that first part of the model, we generally think of that as being structural or deterministic. And so this is what we're hypothesizing that our model form is that would explain the variability that's being observed in our response variable. Okay. Now the error term is capturing all of the randomness, the probabilistic nature of our analysis, the stochasticity, and all the other things that aren't explicitly accounted for in the deterministic part of the model. Okay. And so from our perspective, we're generally trying to estimate what the slopes of these different fixed effects are. Okay. And so when we think about that error term, part of it is just pure residual random error. And then there may be another portion of that that is comprised of what we refer to as a random effect. Okay, so there may be certain individuals that we're observing over time, or there may be certain characteristics that related to our sample. We're not observing these factors, but we know that they have an effect. And if we could somehow collect that information and tease that out, that would basically eliminate reduce some of the random error here and allow us to better determine then what the effects of some of our variables of interest are. Okay, as in all the other prior cases in this class, as we reduce the amount of just random error, we're able to more effectively demonstrate where significant effects exist. Okay, and so there are two general ways we try to systematically control for a portion of that random error. The first of those is by estimating what's referred to as a fixed effects model. Okay. And so when we observe the same individuals or the same units over time, and a really good example of this, if you think about the driving simulator study data that was used in homework assignment 4, we saw those same individuals engaged in multiple trips to the driving simulator, right? And there were probably some people who were more likely or less likely to stop in each of those trips, each of those test drives as compared to others, okay? And so those differences are generally speaking just captured in that random error term, but what if we could actually tease that out to some degree, okay? And so what we're doing here, we're basically looking for any individual I, we're observing that individual at time t, okay? And so our traditional form of the model, we've got a constant term, we've got some x variable that's unique to that individual and maybe unique to that time period as well. We're trying to estimate our corresponding beta. And then we also have an error term that's going to be unique to that individual and to that time period, okay? And so one thing we could do in a fixed effects model, if we're observing the same person 12 times as an example, we could estimate a unique intercept term for each of those individuals in our sample, okay? And so what that does, this is very similar, and I keep coming back to the paired t-test example. So what would happen here, rather than having this one constant term that's applicable to our entire population or our entire sample, as the case may be, we're estimating an intercept term that's unique to each individual. And so what that means, if you think about our regression model, that regression model would be shifted up or down for each individual, because some individuals would tend to exhibit higher values, some would tend to exhibit lower values, and the rest of that model remains as it were previously. Now, the implication of that, though, is keep in mind this error term basically has two parts. It has the pure random noise, and then it has the systemic part. And we're pulling out that systemic part here, and we're directly accounting for that through the estimation of these intercept terms, okay? And so consequently, there are some major advantages that come into play here. First of which, this helps us to avoid the omitted variable bias that may be due to factors that don't change over time. So if we've got some characteristics about an individual or some characteristics about a site, in those circumstances, we're not able to necessarily directly account for those impacts. But if we're observing the same individuals over time, we're basically conditioning our analysis on that fact. Okay, so there are some things we don't observe about the individual. If we think about the crash example, there are some schools that are probably in areas that are just higher risk or lower risk, but with the data we have to work from, there's no way for us to explicitly capture that. And so if we observe that same school 5 times, it might show higher than average crashes all 5 years. or it might show lower than average crashes all 5 years. And so in the fixed effects framework, what we would do is we'd have a constant term unique to that site. And so this variable here, you'll notice it's subscripted I and not T. So you would have the same constant term for every individual during each analysis period. So person 1 would always have the same value, person 2 or observational unit 2 would always have the same value, and so forth and so on, okay? Your Y's could change, your X's could change, but the individual you're observing does not. Okay, so that's an important caveat to introduce there. And so, like I said, the fixed effects model is based on the assumption that each of those units we're observing has its own unique intercept. Now, the one big drawback to that is, let's say we're observing a panel that's got 100 or 1,000 or 1,000,000 individuals. That would mean that we would need to include 99 or 999 or 999,999 different indicator variables as a part of that analysis, okay? And so with very large numbers of individuals or very small time periods, if we're only observing 2 time periods as an example, that's a lot of parameters to estimate, and as a consequence, we lose a very large number of our degrees of freedom, and it can become very challenging to show that anything's statistically significant, okay? And so a more efficient alternative to that fixed effects model is simply that we allow that constant term to vary, but we allow it to vary based upon some known distribution. And so instead of having to estimate 100 parameters, we could estimate just 2 parameters as an example, okay? So we'll look at the model we had started with initially, and we're just basically adding another error term here, okay? So this error term is random. This new error term we've added is random in a sense, but it's unique to each individual I, okay? And so it's essentially analogous to allowing alpha to vary across individuals here, except in this case, rather than having a unique alpha for each individual, we have a unique error term for each individual. And so that's going to basically, it'll have a mean value of 0, and it'll have some variance, which we can then estimate, okay? And so the variance of this error term is basically telling us how much variability there is across individuals in our sample, okay? And so we're able to gain some of the same insights, but we don't have the same level of cost that we would in the fixed effects framework, because we don't need to estimate an intercept for every individual, okay? And so in this case, this unique intercept term is basically drawn from a distribution. It's a random draw from that distribution. It's independent of the traditional error term. And this is where the term random effects model derives from, okay? So we're assuming that those constant terms are basically random draws from a distribution, okay? And so again, the main advantages here, we've got more degrees of freedom because we're not estimating an intercept for every individual person or unit. We're only estimating the parameters that describe those intercepts. So basically the mean and variance, right? The other advantage here, we can also estimate time invariant explanatory variables. And so what I mean by that, in the preceding analysis, if we were interested in knowing about what the effects of some of those site-specific variables of the school are, as an example, since those variables that describe the school might not change over time, we wouldn't be able to include those in our model. And so if you think about this from the perspective of the driving simulator study, under a fixed effects framework, we could have a constant term for every participant from that study. We would not be able to include the age group, though, or the person's gender as a part of that. And the reason for that is because those variables don't change over time within that individual. And so we're not able to estimate an effect. And you can actually see that if you try to estimate such a model in SPSS. And so in a random effects framework, though, since we're simply assuming that those constant terms are going to be a random sample that are drawn from a broader distribution, we are able to accommodate these variables that don't change over time, okay? So there actually is an ability of us to estimate those, okay? The big disadvantage is that we need to assume that those error terms are uncorrelated with the other predictor variables in the model. And so omitted variable bias can be a concern in random effects models. And so that's one thing to be aware of. Now, unfortunately, it's often difficult for us to tell whether or not omitted variables are a problem because of course we're not observing those variables that are omitted. But that would give certain contexts where you'd be particularly concerned with omitted variables. It may be more appropriate to use fixed effects versus random effects. So you're trying to balance these advantages versus these disadvantages for the random effects versus fixed effects, and then vice versa for the fixed effects. Okay. And so to that end, if you're expecting that you have unobserved variables, it would make sense to use a fixed effects models. If not, you're generally better suited to use the random effects. There are some formal tests that can be used, and these are included as a part of statistical analysis programs to try to assess whether there's correlation, and sorry, that should say between the U's, in the context, in the fixed effects models, whether there's correlation between the constant term and the X's. And so depending upon the result of that text, we can use that as an indicator as to whether a fixed or random effects framework is appropriate. Okay. And so if we think about these two different families of models in concept, fixed effects, so these are repeatable in nature. So we're assuming that those fixed effects remain the same. Every individual has that same fixed effects across every time period. The random effects, again, are just randomly drawn from that distribution, and so that's not the case in that circumstance. The fixed effects we can also think of being systematic in nature, and so again, those same individuals are always prone to observe, higher or lower values of that dependent variable of interest. In the random effects framework, it's random, and we're assuming that these sites are just drawn randomly from a larger population. And then to that end, in the case of fixed effects, we're generally, when we think about trying to draw inferences about the broader population and trying to extrapolate, we can do that in the random effects framework, but in the fixed effects, we're really constrained and we're not as easily able to forecast outside of that sample that we estimated the models for. And that should make sense if you think about it intuitively, is you have constant terms for each individual site. And so if you have a new site, well, what's its constant term going to be, right? In the case of the random effects model, we can use simulation and we can draw a value for that constant term. And so there are some definite advantages in fixed effects if we're trying to figure out cause and effect type relationships within the sample. But if we're trying to extrapolate beyond the sample, there are advantages to the random effects framework. Okay, so those are just a few important things to think about here. And to that end, fixed effects are those in which the populations we wish to generalize are precisely represented in our analysis. So if they're explicitly accounted for in that analysis, we're okay. But if there are groups that are not accounted for, it's difficult to try to extrapolate that more broadly. Okay, and then the other minor issue we'll run into here is that those fixed effects can be continuous, but those random effects are generally going to be categorical. Okay. And so we can think about repetitions. Are they a fixed effect or a random effect? So if you're observing the same individual multiple times, that is repeatable, it is systematic, it's semi-continuous, and you're exhausting the whole population. So if you're looking at those repeated applications of the same individual over time, yes. Now, in the case of individual subjects, can we treat those as fixed effects? Oftentimes not, because repeatability may be an issue. You're observing just a small subset of the population. And so as a consequence of that, we're generally taking the data from this sample and we're trying to draw inferences about the broader population. And so oftentimes, it may make sense to treat those individual subjects as a random effect, and then repeated measures on the preceding example would be thought of as fixed effects. Okay, and so real quick, just as we wrap up the lecture here, we have what are referred to as random intercepts, and then we'll also look at what are referred to as random slopes. And so When we talk about the random effects model, what that basically means is we're estimating random intercept terms. And so this is just basically showing if we collect observations from a number of subjects over time, we'll see variability in our Y variable in terms of those measurements from subject to subject, okay? So we don't see the exact same trends across all individuals. And likewise, if we look at Y versus X across individual subjects, each of those subjects may show a slightly different relationship between Y and X, or in some cases, significantly different relationships, right? And so if we go across that entire sample, it's probably unreasonable for us to expect that you'd see the exact same intercept and the exact same slope for every individual. And so in the case of the random effects model or the random intercepts model, instead of assuming the same general relationship applies to all individuals, we assume that that general relationship applies to all individuals, but some individuals may tend to experience higher values of Y, some may tend to observe lower values of Y, as an example, okay? Likewise, we could see cases where we have both random intercepts and random slopes. And this is getting a little bit beyond the scope of what we'll have time to go through over the remainder of the course. But there are some ways that we can also, much like we would assume that the distribution of the constant term follows some known distribution and we're interested in the mean and the variance of that distribution, we could assume that each of our betas, each of our parameters has a mean value and also a variance associated with it, okay? And so that's the direction that a lot of the contemporary research is heading currently, okay? And so what I'd like to do at this point is pull this back into remote desktop real quick. And I can give you a very brief demonstration of how this works. So there we go. Oh shoot, where did it go? Can you all see my remote desktop now?
You're good.
Okay, great. Okay, so what I'm going to do now at this point, I'm going to close that analysis file. Okay, and so this data set should hopefully look very similar to all of you. So these are the data that come from our driving simulator study, okay? And so at the onset, I'm just going to go in, and previously you had estimated these models either under regression, binary logistic. You could also do it under generalized linear models. There's also a third area we can go. If you go under mixed models, this is where we would estimate this broader family of models. We can go mixed models, generalized linear models. And so from here, what we're going to do, we are going in and I'm going to estimate a logistic regression model for whether or not that driver stopped when they confronted the yellow light, okay? As a part of that, the variables I'm going to include, let's just say as the starting point here, we'll keep it nice and simple. We'll include the age, so middle and older, we'll use the young group as our baseline. We'll compare females to males. And then here I just have the sequence of drives. So the first drive, second drive, third drive. And so I'm including the second and third drives here under the assumption that there might be some kind of learning effect on the part of the individuals, okay? And so you don't need to worry about either of these latter tabs here. So it's just basically determining your target variable, which is your Y variable, your fixed effects. We'll return to the random effects momentarily, but we hit run here. And we see our cross classification table here in terms of how predictive that model is. And then we scroll down here and looking at our results, it looks like there are moderate differences between the middle and youngest age group. And it looks like older drivers are more likely to stop. In their case, that's not significant at 95%. It's getting reasonably close. We also see that female drivers are more likely to stop for whatever reason. And then lastly, and somewhat interestingly, we see that people tend to be less likely to stop on the second and particularly the third drive through the simulator. And so I would presume this is some type of learning effect. So once the drivers are in the situation, where these red lights are arising. They eventually adapt to the situation, and so for whatever reason, over time, they tend to be less likely to stop. Okay. And now a question that arises here is that we are observing the same individuals, 12 times roughly over the course of those 3 different drives in the 4 different scenarios. And so what we can do, if we go into that same mixed models on the first tab, and I had skipped over this initially, it talks about our data structure. And so we have a subject variable here, which is basically a unique identifier that corresponds to every subject that's in our analysis, okay? And so there are 2 different ways we can try to accommodate that individual in our analysis, okay? The first of those is we could estimate we'll start with the random effects model here, okay? So what I'm going to do, I'm going to go under random effects. I'm going to add a block, and that basically means we're going to add a constant term here. So I'm going to define the subjects based on that subject variable, okay? And then I'm also going to include an intercept term here, all right? And I am going to structure this. I'm going to hit OK, hit run, and then we'll see, compared to the normal output that was just observed, when you get the output here, it's telling you, so this is for the first subject. So that subject was observed, subject 1 was observed multiple times. Interestingly, subject 1 stopped every time. So that's just the first time you see that, it might raise a red flag, but it seems to be okay here. There are 49 levels, which means there are 49 different individuals that were observed there. And so we see the same general output we had previously. In addition to that, we see our model output. Now, interestingly, as you'll recall on the preceding analysis, the p-values for the older drivers and the female drivers were very close to that 0.05 threshold, okay? However, what appears to be happening here is that once we control for those individuals, those effects largely dissipate. Okay, so it was probably the case that it wasn't necessarily that females consistently were more likely to stop. It was probably that there was a small number of females who those individuals were consistently more likely to stop. The same thing for older drivers as an example. Interestingly, that learning effect still appears to be there. So we do see differences between drives 2 and drives 3. The other important piece of input we see right here, as we go down to our blocks here, we have actual estimates then for our random effects, okay? And so I'll scroll back up real quick. So we have this intercept term, negative 0.774. And so that's basically an estimate of that, the average value, the mean of that intercept across our sample. We also have an estimate here of the variance of that intercept term, okay? And so we see significant variability. If we took the square root of this, we could then multiply that by 1.96 or roughly 2 to get a 95% confidence interval. But the main takeaway here is that there is significant variability across individuals, okay? So what's happening here is we're conducting a hypothesis test to see whether or not this variance is significantly different from 0. Okay, and we can see very much that it is in this case. And then so that suggests that the random effects model is a good fit here. We can also test the fixed effects model here. And so the way we're going to do that is we're going to come back in. I'm going to remove this random effect because we, again, are not working in that random framework. And so for the fixed effects, all I'm going to do, I'm going to take that subject variable and I'm going to use that as a parameter in my model, okay? And you may not realize what that's going to do, but what it's basically going to do here, it's going to estimate in a unique constant term for each and every individual. Unfortunately, we should run into a problem here. And so you'll notice the note here, and sometimes this is an issue, sometimes not. But there's a quasi-complete separation in the data. The maximum likelihood estimates do not exist, and ooh, that could be a problem. So what's going to happen here? We're going to scroll down, and as we scroll down, a few things come into play here. So first of all, if we look at that middle age group, we've got a major problem with the coefficient and the standard error. If you see a standard error of 17,000, that's probably a cause for concern here. Down below that, we have, these are basically constant terms for each individual, okay? And so what we'll find, generally speaking, some of those individuals are held out, so we don't over-identify our model as an example. So you always need to hold out at least one observation. But as you look at the individual subjects, some of these constant terms are problematic as well. What's probably happening here is that these individuals are either always stopping or they're always going through the intersection, okay? And so linear regression might have been a little bit better way to demonstrate this, because this would be less of a problem in linear regression because it's significantly more likely we'd see the same 0-1 fit than the same outcomes for a dependent variable in a linear regression model. But I just wanted to demonstrate that. Now we can rerun this. And so if we look at these problems that arise up here, part of the reason for that, and when we talked about fixed effects models previously, since the age and the gender of that individual don't change over the course of this analysis, those are definitely going to be problematic for us. And so what you would be advised to do is to not include those types of variables in our model. And so we can rerun that. And then as we scroll down, so these top 3 variables in our model, so those are fine, there's no problem there. When we get to the individual constant terms, we do run into issues here, and there's no way to work around this other than what you could do is you could remove these individuals from our sample. So if we remove subjects 1, 17, 19, 26, 34 and so forth. So any of the observations that had very large standard errors, we could rerun that analysis and then we'd actually see results that made sense and were generally consistent. Okay, so as you can see here, some people were significantly less likely to stop and that was consistent, and then some were significantly more likely to stop. Okay, and so that is a very quick intro into fixed effects and random effects models. And so for those of you, if any of you are observing this type of phenomenon where you've got the same unit that's being observed multiple times over the course of your study, this would be a promising avenue to potentially look at to control for some of those analytical concerns that would arise, okay? So we're right at 9:50, but let me see if we've got any questions. Okay, I've got one. Do you have a way to remove, filter out individual data via SPSS, or do you need to remove it manually from the data set? Yeah, so we can. I would probably suggest that you do that manually, but let me show you how you could in concept do it. So if you go under data, select cases, we could go if subject is equal to 1, or, and then it becomes a very long statement. Subject is equal to, I don't know, I've lost track of 14, and just a series of or statements. You could do that. And then you just want to make sure you can either filter out the unselected cases, or you could keep the unselected cases. You need to figure out what your filtering criteria are here. But so that's the way you would do it in SPSS, or at least that's the way I know how to do it. There may be some other flexibility there. But the easiest thing to do would probably just be to go into Excel and pull all those, or alternately, you could use some kind of coding logic structure, okay? Falarin, you've got a few questions. I guess we're at 9:51, so if any of you need to bail, I will be posting this later today along with the last lecture from last week. My apologies, I haven't got that up yet. But Falarin, questions on the fixed and random effect stuff?
Yeah, fixed and random effects, and also on some other stuff. So I saw that when you were talking about the likelihood of them stopping, I think I might have misunderstood that or like messed it up in the homework or something. So if your response variable is drivers that stop, then if the coefficient is negative, does that mean that they are less likely to stop?
Correct. Now you need to be a little careful because I think we talked about this. There are at least 3, if not more, different options you can use in SPSS to estimate these models. And in some of those frameworks, by default, SPSS estimates the logistic regression such that the y variable is equal to 0. So you interpret, or it provides results that are backwards from what we would expect. And so that's a setting that you would need to change. If you go back to my logistic regression lecture, I walk through how to do it on there. But I guess, Falarin, the short answer is depending upon which method you used, you may have done it incorrectly, and you may not have. I'd have to take a closer look there. So I guess if you hold on and just give me a sec, I had to transition to downstairs because my wife had a meeting. So I will quickly try to demonstrate that off the top of my head. Okay, here we go. Okay, so in SPSS, you can estimate the mixed model I introduced previously and the generalized linear models. By default, it sets that up correctly. If you go under regression binary logistic, if I'm remembering correctly here, so here, if I take that stopped variable, let's see if that, and apologies, Falarin, I wasn't necessarily prepared for this question. But yeah, so you'll actually see those are coded backwards in this case. And I'm trying to remember off the top of my head how we correct for that. But is that where you're going with that, Falarin? Did you know?
Yeah, that's what I'm asking.
Okay, so I think it's under, no, not options, somewhere here.
I think it's for the generalized linear one that you can change it, if I remember well.
Okay. Okay, yeah, so here you definitely can. I thought there was a way you could trick it under. So yeah, the reference category you can set as lowest value or highest value here. So it defaults to the highest value, which again is the silliest flipping thing you can imagine. But I thought there was a way we could trick it under the binary logistic even, but maybe I was mistaken.
So yeah, my question is just that the lowest value, is that supposed to be like the 0, or I'm a bit confused?
Yeah, so when we're estimating logistic regression models, you would want to set it up so that your base case is 0 and your parameter estimates would be reflective of if that variable were equal to 1. So you'd want it coded 0, 1 rather than 1, 0, if that makes sense.
Okay.
Okay, and it should be obvious as you start working through. It quickly becomes evident if everything seems backwards from what you expect it would be going in. That's kind of a red flag. Now, if it's a data set you're completely unfamiliar with, it could be a bit of a learning curve there. But again, I have no idea why SPSS is programmed in that manner. But yeah, just by default, some of the platforms assume you're interested in the zeros rather than the ones. But generally speaking, if you're presenting these results in a paper, you should definitely present them such that you're estimating it with the 1 as compared to the 0 and not the 0 compared to the 1, right? Because it just makes sense intuitively. if you're estimating a model for driver stopping behavior, you won't want to present results that correspond to drivers not stopping, right?
Okay.
Okay. Did you have any other?
Yeah, I have one more question. So, I noticed that sometimes when you run the models, right, we have some variables that are not significant. So, and sometimes the coefficient kind of makes sense if you think about it. So, do we keep them in or remove them? I believe we cannot use that for like, say for like predicting something.
Okay, I know where you're going with this. Great question. And you would see different responses from different individuals. Generally speaking, I would include a variable in my model if it wasn't significant, but if it was either of practical interest. So if it's something that you assumed would have had an effect but didn't, it would be useful to show what that mean effect is and how close or how far from being statistically significant it was. So that's one reason. Secondly, if the magnitude of the parameter estimate is relatively large, it might be, for example, that a variable looks to have a positive or a negative effect, but there just might be a lot of noise with that variable. So the standard error might be very large. So as an alternate, you may also want to include now, when I say very large, I don't mean 17,000, like clearly there's an erroneous issue here, but let's say if in a logistic regression model, if you had a beta of like 0.7, but your standard error was like 0.5, so that's just saying that it looks like there's an effect, but that effect is fairly variable across the sample. So I should preface that, though, again, that not everyone's going to give the same feedback on that, because I've published papers before where a reviewer will say this variable is not significant at 0.05, you should remove it from the model. And I generally politely disagree with that very forcefully. Because let's say if you run an analysis and your p-value is 0.051, okay, so if we're just going to stick by hard and fast rules, you throw that out. And when you throw that out, that does several things. First of all, you're showing a result that is very close to being statistically significant. And so this gets back to, we had talked, oh gosh, probably a month and a half ago at this point, about the use of p-values and how that can be a little bit hazardous. And so ultimately my view is you present the results to the reader, you discuss them in a manner that's transparent. And so if you've got variables that aren't statistically significant, I think it's worth noting that and just saying that it might be interesting why that's the case. But then at least the reader can look at the results and make an inference of, well, if it's 0.051 and we conducted some additional investigations here, it's very likely that result would then be statistically significant if the sample size were increased, as an example. But then also all the cards are on the table. Now, with that being said, I don't want to encourage everybody to include every variable in your model, because by that same token, just based on probability in sampling theory, you're going to have some variables that might be significant at 95% confidence that they're just type 1 errors. Now, do we know that they're type 1 errors? No. But please don't include 100 different variables, because that's everything in your data set. So you want to be somewhat selective, but Folarin, I guess, as a general response, if you think the result is interesting or insightful, or you think that variable could or should have had an effect, but it didn't, I would still retain them in the model. And if it's more nuanced, I'm happy to talk through specifics with anybody. So does that make sense?
Yeah, thank you.
Yep. Okay. Any other questions? Sorry, we're past 10 o'clock now at this point, but I will entertain any
Hey,
last
Dr. Sai, I have a
question.
small question.
Yes.
So suppose we fit one regular model and one random effects model, and we see that one of the predictors is not significant in random effects model, but is significant in the other one. So what is that telling us?
Okay, so there is a bit of nuance that's potentially coming into play here. So if a variable is significant in a naive framework, i.e., where you're not considering random effects, you're just estimating a normal model. And then when you estimate the random effects model, it's no longer significant. One potential explanation there is that you have certain observations that may be having a disproportionate influence. And so as an example, the big concern, if we have repeated measurements on the same subject over time, if we don't account for that, it's very likely that there is going to be some correlation that's present there. And that correlation could manifest itself in one of several ways. One way is that if you observe the same individuals multiple times, the model doesn't know that those variables are correlated, right? And so the model just assumes that all of those observations are independent. And so your error term is assumed to be homoscedastic or constant across all those observations. But what you're going to see is that that same individual, if you observe them 5 times or 10 times, the residuals are going to consistently be higher or lower for that individual. Okay. Now, when you control for that by estimating a random effects model, that essentially it corrects for that because you're adjusting the constant term. And when you adjust that constant term, the residuals aren't going to consistently be very large or very small. They should basically be random, right? So they'll be random just like they should be in theory. And sorry, this is turning into a very rambling answer, but the consequence of that is if you don't use the random effects framework, you are tending to underestimate the variance. And so you may end up finding a significant effect that isn't actually a significant effect, if I'm interpreting the nature of your question correctly there. So that's the one big concern, is almost any time you estimate a random effects model, you're going to find that your p-values will tend to be larger than if you did just a naive pooled model. Now, with that being said, there are different sets of concerns that could arise related to omitted variables as one example. And so I guess, Nishal, if you're talking specifically about the data you're working on, one workaround to that is that instead of including each observation 5 times, if you can combine those 5 observations, and so if you look at that average over 5 years, or the sum even better over 5 years, if we're talking about crash data as an example, that would be another workaround. Now, because another thing to keep in mind here, and this gets very nuanced, we could very easily have a whole second course on research methods. But as you increase your sample size, that's generally advantageous to us. But also as you increase your mean values, that also tends to be advantageous, because typically for most variables, as the mean increases, the variance, it may decrease, but if it doesn't decrease, at least its ratio relative to the mean will decrease. And so you'll tend to be able to tease out significant effects more easily if you aggregate the data. And so if you looked at total over 5 years instead of each of the 5 years individually. Now, in some research questions, it probably doesn't make sense to combine those 5 observations or the 10 observations. So in the case of the driving simulator study, I wouldn't suggest that you add up the 12, the number of stops among the 12 for an example there. You're probably better off analyzing it at that greatest level of fidelity. But the short answer to your question is the random effects model is probably doing a better job of representing whether or not there's a significant relationship. And then the second point is there might be some additional nuance and some other avenues that you could investigate. Okay.
Okay, thank you.
Yep. All right. Any other questions? Okay. And again, we're well over time. So Wednesday, the plan will be, and moving forward, I'll show up and we can answer any and all questions that would relate to the research projects, and or just general questions you have on statistics that we haven't gotten a chance to cover over the course of the semester. So I guess in the meantime, I know some of you are still working on the preliminary results. So I guess just pass me a quick note to let me know once those have been submitted. I'll try to give everybody some quick feedback and direction once that's submitted, just so everybody's in fairly good shape. And then, like I said, we'll basically have until a week from Friday to get those presentations in. And I'll set that up in D2L shortly, and then the papers will be due that following Monday, okay? So barring any other questions, that's all we have for today. Thank you all very much. Have a good one.